Now let us see some of the very important results related with the matrix multiplication. The first one is, for two matrices A and B, the various possibilities are: first, AB exists but BA does not exist. Second, BA exists but AB does not exist. Third, AB and BA both exist but they are not same, that is AB not equal to BA. So this third property basically it means that the matrix multiplication in general is not commutative. And the fourth case is, both AB and BA exist and they are equal, so that is AB equal to BA. So these are the various possible cases for any two matrices A and B. Now moving on to the next property, A into BC is same as AB into C, which is called as the associative law. That is, we can associate any two adjacent matrices and complete the multiplication. Next one is what is called as the distributive law. That is, if we have a product of a matrix A multiplied with either addition or subtraction of two matrices B and C. So A into B plus or minus C is equal to AB plus or minus AC. So it's like as we do in algebraic opening of bracket, the outer matrix A is multiplied with both of the matrices inside, and that is connected with the operation which is inside the bracket. Now moving on, we have the next property that if we have the product AB equal to 0, that is 0 matrix, then it does not necessarily mean that at least one of the matrices A and B is a null matrix. Now this is on the contrary to what we have in algebra. That is, if in algebra when we say that product of two numbers is 0, then it definitely means that one of them, at least one of them, has to be 0. But here in matrices it is not the case. Moving on to the fifth property, AB equal to AC does not necessarily mean that B is equal to C, even if A is a non-zero matrix. So that means if AB equal to AC, then we cannot simply cancel A from both sides as we would have done in algebra. So we cannot just cancel A from both sides and say that B is equal to C. It may happen that B is not equal to C. So therefore in general cancellation law does not apply in matrix multiplication. In the sixth one we have A square, which is nothing but the product of A with itself, and this can be extended to any degree of A. That is, if we have A cube, then it is a product of A taken 3 times, and so on. In the seventh property we have A plus B the whole square, which is nothing but the product of A plus B with itself. Now here, while doing the product, the only difference from the corresponding algebraic counterpart is that if we do in algebra, that is x plus y the whole square, it's x square plus 2xy plus y square. But here, since the products AB and BA need not be same in general, therefore the middle term cannot be just clubbed together with AB plus BA as 2AB. Therefore we have to keep these two terms AB and BA as separate only in general. Of course, if they are given to be same, then we can club AB plus BA together, but otherwise not in general. Now the next property, eighth one, says that the determinant of product of two matrices is equal to product of the two individual determinants. And this property also can be extended to product of any number of matrices, that is not just 2 but 3, 4, or in general any number of matrices. And lastly we have if we have k as some real number, and if n denotes the order of the matrix A, where A is of course required to be a square matrix, then the determinant of Ka is equal to k raised to n into determinant of A. So these are the properties that we have to keep in mind while solving the sums based on the matrices.